One of the effects of surface tension is what we call capillary action. And the way that works is that, let's say we have a little cup of beaker of water here, and we stick a very thin tube, let's say a glass tube, in the water like that. What will happen is the water will come up and reach a higher height inside the tube than is outside the tube. And of course, that would violate Pascal's principle. But the reason it does that is because there's some capillary action taking place. There's some interaction between the molecules of the water versus the molecules of the glass. And in the case of a glass-water interface, the water molecules are being attracted to the glass more strongly than they're attracted to each other. So there's more adhesion, as we call it, between the water molecules and the glass surface than there is cohesion, which is the forces between the actual molecules themselves, which causes surface tension. The way you want to technically look at that is there's really three forces at play here. There is a force between the liquid and the surface. There is the force between the surface and the air. And there is a force between the liquid and the air. And all that contributes to how high the water will go inside the tube. Now, in this particular case, what we find is we use mercury and we stick a small little, what we call capillary tube inside the mercury. What will happen then is the mercury inside the tube will actually be pushed down below the level of the mercury in the rest of the cup. The reason for that is that the mercury molecules will attract each other more greatly. That would, of course, be the force of cohesion is greater for mercury than the force of adhesion between the mercury and the glass. So therefore, the capillary action works then in the opposite direction. It's kind of difficult to figure out how to use this, and of course, since the force is proportional to the coefficient of surface tension for the three related surfaces, it is easier to look at it like this. What we can say is we have a hard time measuring or computing these two quantities. But what we can do is that there's look at it, that there's a balance between the forces. We know that there's going to be an upward force in this direction caused by the surface tension, let's just call it ST, between the liquid and the air. So that's the surface tension we're used to, and that is 72.8 dynes per centimeter for water, 20 degrees centigrade. Now notice, of course, we only want to consider the component that's perpendicular to the horizontal. So then this would be what we would call the force times the cosine of theta. Theta here, of course, is the contact angle. You can look at it on either side. What that means then is that this component of the surface tension then is counterbalanced by the weight of the additional water that's being pulled above the level of the water right here. So this here is a certain amount of mass of water that you have, and of course that then contains a certain weight of water. And so what we can then say is that the force of the surface tension times the cosine of the angle must equal to the extra weight of the water that then gets pulled up into the tube. So if we now assume that the radius of the tube is r, and the height of the water above the rest of the level of water is h, then we can probably go ahead and find a relationship to calculate what the height of that will be, and that will be related, of course, to the coefficient of the surface tension and the density of the liquid, in this case is water, and also on the radius of the tube. All right, let's do that. First of all, the mass of the water, that would be equal to let's see, let's do a connection here. We have density is equal to mass divided by volume, which means that mass is equal to density times volume. So we can replace mass by density and volume. And the force of the surface tension, that can be written as the coefficient of the surface tension times the length along which that surface tension acts. And in this case, that length would be, and let me use a different color here, that would be all along the edge of the glass. So if you can imagine that this would be going all the way around the glass, you can now I'm kind of maybe confusing a little bit. This was supposed to be the meniscus, but you can also think of the water at the top along the edge, and so let me go like this, along the edge like this, will also feel the surface tension all around like that. So this is the force caused by the surface tension, which is the total force along the edge of the glass, which is then counterbalanced by the weight of the water being pulled up into the tube. So the length would be the complete circumference of the tube. Let's see here. That would be times the cosine of the angle theta. Now it turns out For the contact angle between water and glass, that angle is pretty well near 0, so we can call this equal to 1, and we can ignore that, and that would be equal to m times g. Now, of course, m, I'm going to replace that by rho v, so we have rho v g. All right, so now plugging in what the length is equal to and what the volume is equal to, we get the following. So the coefficient of the surface tension times 2 pi r, which is the total circumference of the tube, that's the contact length between the water and the edge of the glass, is equal to the density of water times the volume. Now the volume would be the height times the cross-sectional area. That would be pi r squared for the cross-sectional area times the height times g. Now notice that we have a pi on both sides of the equation. That cancels out. We have an r here and an r squared there. That cancels out. And we want to calculate the height. We want to find out how high the water will rise in the tube. So if we divide both sides by rho, r, and g, then we get, and turn the equation around, we get h is equal to the left side, which is 2 times the surface tension of the water, divided by rho, divided by r, and divided by g. And that will be the height of the water that gets pulled up into the tube because of the action between the water and the edge of the glass, pulling that up. And so we have that surface tension causing this amount of water to rise up and giving it that height. Now notice, the smaller r, the higher it will go. So if you take a very thin capillary tube with a very small inner diameter, it can actually go quite high. The density, of course, if we use water, that's 1,000 kilograms per cubic meter, or if you use another fluid that has higher or lower density, that will, of course, also affect the height. Acceleration due to gravity, that will stay the same on the surface of the Earth, and of course, the coefficient of the surface tension. Now, what happens is if you heat the water, this will go down, and so the height will drop. If you put some soap in the water, this will go down, and the height will drop as well. So it does get affected by the coefficient of surface tension. But that's how capillary action works in very small little tubes, and that's how you find how high it will go in the tube.